very excited to talk about this. This is one of the first few times I've presented this. It's very preliminary work, so I'm excited to get everybody's feedback here. I was saying earlier, I'm out of my depth in two dimensions here, both doing kind of uh, work on environmental related stuff and also historical stuff. So please feel free to give me all of your feedback. Okay, so the see, I can change my slides. The kind of motivating observation here is that deforestation was underway long before the Industrial Revolution happened. And we can see this, this is from my data, we can see this just by plotting the share of forest cover globally, going back 12,000 years all the way up through the Industrial Revolution. So we see this kind of, say 7,000 year run up in declining forest cover. And this is the motivating observation here. In particular, what I'm asking in this paper is why we saw this sustained decline in forest cover globally prior to the Industrial Revolution. And a bit more specifically, I'm interested in one candidate source of change in forest cover historically, which is kind of the development of agricultural technologies. So I'm interested in whether agricultural technologies mitigated or accelerated deforestation in this period. This is a fundamentally ambiguous question, and the reason is as follows, so just to motivate this. So prior to Industrial Revolution, the farther back we go, we think there's kind of limited regional or even non-existent regional trade. So it's a very different world from the one we live in right now in that respect, also other respects, but certainly in that respect. And on the other hand, this was a world with Malthusian population dynamics. And these two forces will tend to, for reasons I'll describe, will tend to work in different directions, or they'll tend to kind of, um, what do I want to say? They tend to have interact differently in opposite directions with developments in agricultural technology. So in particular, improvements in agricultural technology, this is the kind of what the environmental literature tends to think, are influenced by trade. So you kind of expect in the presence of trade a high price elasticity of agricultural output. Um, and that tends to make improvements in agricultural technology reduce forest cover, and then the kind of competing force, of course, is that in a Malthusian world, right? If we have improvements in agricultural tech that raise standards of living, this raises the population, um, and that has competing effects on forest cover. So empirically, how I'm going to tackle this is starting with one kind of macro agricultural tech shock and one micro agricultural technology shock. I'll describe what these are. Excuse me. And I will measure the effect of these shocks on forest cover using fossil pollen records that allow us to reconstruct forest cover for the entire Holocene period. The outline of the talk is straightforward. I'll start with a model to motivate this question a bit more formally. I'll then study the kind of macro technology shock. This is the macro shock to end all macro shocks in terms of agricultural technology. So that's the first agricultural revolution. And then I'll zoom in on a somewhat more modern case study, which is the introduction of the three-field rotation system, which happened kind of around the medieval period. So starting with model. Now, I'm going to develop what I'll describe as a dynamic equilibrium bioeconomic model of a pre-industrial economy. This is a world that has, in the model that has limited trade and as a consequence, a relatively inelastic demand for agricultural output. And for reasons I described, I'll get to this in a moment, right? This interacts interestingly with improvements in agricultural technology and also Malthusian population growth, which is going to tend to make the demand for agricultural output more elastic. And this is where the kind of competing effects are coming from. To get a little more intuition, this is not from my model, it's just lifted from another paper. Basically, the idea here is that in the left panel, you see kind of market for agricultural output with an inelastic demand curve, and on the right, relatively elastic demand curve. And the boxes represent what's happening to revenue uh, for uh, agricultural producers. And so basically, when you have this inelastic and therefore incentives to kind of clear forest land. So in the case of elastic demand, we can see that an increase in the supply and the kind of a supply shock, let's say an agricultural technology shock that shifts the supply curve to the right, can potentially make agriculture and clearing forests as a consequence more profitable and thus kind of incentivize uh, clearing forest land. So this is the source of the kind of, at least in modern debates about this question of why there's this ambiguity.
As- Uh, Tristan, can I
Yeah.
ask you that in that figure, this is very basic one, but at that period, so I'm just wondering what is the price of the agricultural product because people are not trading, so and the agricultural products are, I think that's the main thing that people store, so itself is kind of money or so.
Yeah, that's a good question. So I'll get to this in the context of the model, and also it's a little bit contingent, right? So
Mm.
when I talk empirically about the first agricultural revolution, the Neolithic revolution,
Mhm.
I think that's exactly right.
Oh.
The right question to ask. When we talk about the medieval period, so I'm not a historian, but I think there is probably something closer to there's certainly like trade within towns, let's say,
Mm.
from the output, kind of agricultural output. So I think at least in the kind of more modern, more recent pre-industrial
Mm.
setting, we can think about
Mm.
something more like a
Mm.
price. But I think that's a fair critique in the context of kind of earlier settings.
Right.
I
Right.
should say, since this is very new,
Mhm.
the model you're going to see has kind of some of the trappings of a more modern. It has explicit features from a pre-industrial setting, but also like fairly well-defined property rights, which is another kind of thing we probably don't see as much in the very early setting. And so
Mhm.
I'm
Mhm.
as you listen to me talk about the model, I'm very interested in thinking about how I could kind of represent this type of economy a bit more
Yeah.
accurately than I'm doing. So that's
Yeah.
a critique to keep in mind as you see the model.
Mhm. Mhm. Oh, yeah.
Okay.
Thank you.
So let me describe the structure of the model. We'll start with households. Households have a simple utility function over consumption of an agricultural good and consumption of a non-agricultural good indexed by A and N respectively. I assume a kind of what I understand to be a standard law of motion for population, P, which depends on the deviation of per capita agricultural consumption from some subsistence benchmark. I'll next describe the two sectors. So there's an agricultural sector. Excuse me. I assume that agricultural output is produced with agricultural technology, um, agricultural land, that's L, kind of confusingly, L sub A, and agricultural labor, which is H sub A. The non-agricultural sector has the following structure. So we have non-agricultural output, which depends on the level of productivity there. Energy use, so that's going to be important, and also non-agricultural labor, that's HN. The E is the interesting thing here that makes this model kind of non-trivial, right? So energy that's used in this sector comes from uh, output in the forestry sector. That's Y sub F here. Think about that as kind of timber. That in turn is produced using agricultural land, which is then harvested. So L sub F is, sorry, forest land, I misspoke, is L sub F is forest land, and H is, let's say, per hectare biomass or harvest. It's the mnemonic there, right? So you harvest on forest land, and the kind of product of those things is the amount of uh, forest output that's produced. There is then on top of this a landlord. So this is where this kind of sounds more like a medieval setting, which is maybe more germane to the second empirical application that I'll talk about than the first, uh, who rents out land. So there's a fixed stock of land that's allocated between agriculture and forests. And that landlord maximizes profits from that land by equating rents in these two sectors.
Tristan, can I ask you something?
Yes.
So here, when you say like the harvest from the land, I assume it's an infinite supply. There is no, so should I assume that as a non-renewable resource, as a renewable resource, or how should I think about this?
So I have some more on this on the next slide. So let me
Okay,
show you that, and then we can revisit the question if
thank you. No.
yeah. Yeah, so the final component of this, this I alluded to earlier when I was talking about property rights, the tenant forester. So you can imagine a tenant who's renting forested land or 1 hectare of forested land from the landlord who owns it. Um, each hectare of forest land has biomass, stock, capital S, denote by lowercase h the harvest per hectare. And then there's this kind of biological law of motion that relates the growth in the stock, the biomass stock, to harvest, which detracts from that, and some like organic growth term. That's the G of S you see here. And so total forest biomass is then, that is like in the aggregate, S tilde is the aggregate thing, whereas S without a tilde is the per hectare object. So the kind of one of the interesting objects of analysis here, the thing that I think most closely corresponds to the empirical object I'll be talking about, is this S tilde, right? And then the tenant forester is going to solve this dynamic programming problem of choosing the harvest level for, the hectare of land that they're on to maximize the present discounted value of their profits, which is the difference between the price that they're able to sell this, harvest for in the market. This gets to the question we were just looking at, less some costs of harvesting and less the rent that they have to pay to the landowner. And there, of course, I guess I shouldn't say of course, they internalize, and this need not be the case, right? We could drop this, but they internalize the law of motion for the forest land when they make this decision. I focus throughout, I think, for the remainder of what I'm going to show you, on a steady state where we think about a constant per hectare stock of forest land and a constant population. So everything I'm going to say is kind of in that world, which yield, I think, most interestingly, looking at the second line here, an agricultural price, price of agricultural output that is a function only of the subsistence level of consumption. And this is, I think, a really interesting feature of the model. In some sense, it's trivial to see when you write down the math, but right, this basically looks like you're getting is, at least in the agricultural sector, a perfectly elastic demand curve for agricultural output as a result of the Malthusian assumption here. So this is I think important, and it suggests that the Malthusian stuff is really important in this model. The debate in modern settings about this question, and then there's an active debate about this, what is the effect of improvements in agricultural technology, is centered around this elasticity of demand that I described earlier. And as you see here, really in a simple way, that thing is kind of goes to the limit, if you will, right? We have this perfectly elastic demand for agricultural output directly as a consequence of the Malthusian assumption. So this is really important for explaining forest dynamics in the pre-industrial setting. Functional forms. So I endeavored to find not excessively complex, but at least somewhat plausible biological growth function for the stock of forest land per hectare, which is what you see here. This is the monomolecular form. And there's a kind of biomass dependent harvesting cost, which I've written here. And that's also going to be important here. So you kind of immediately see that the harvesting cost falls as the stock of biomass goes up, which is kind of the natural, I think, assumption here. This is also a kind of standard but simple form for the harvesting cost. Okay, so that's basically the model. It's not super sophisticated. To be honest, I'm not totally sure how controversial the setup is. This seemed like the most organic way to write this down for me, but I'm very much open to suggestions about why this is implausible or why I can model this better given the setting. But that's what I'll be talking about for now. So a central proposition that comes out of this, and I think this is the interesting prediction of the model, is that improvements in agricultural TFP reduce forest land if and only if the level of agricultural productivity exceeds some threshold, where I can express that threshold as an explicit function of model primitives, which you see here, I think most of which I've explained. Maybe I've left out a few. And that's precisely it's precisely the kind of motivating observation here, which is that there is this fundamental ambiguity that we see in the effect of agricultural productivity on forest land. So a few comments on this. Right, this implies a non-monotonic effect at low productivity levels. Right, but since ZA is unbounded, right, the kind of implication is that at least if we forever live in this world, and we're kind of transitioning between steady states identified by a level of ZA, and that thing keeps progressing forward without a change in the underlying structure, deforestation is going to be inevitable here. You basically get past this threshold, and then further improvements in agricultural tech are going to lead to declining forests. Another comment on this is that you might be asking, right, that the proposition is stated in terms of forest land, but probably the best analog to the empirical object I'll be talking about is forest biomass, which is the product of forest land and biomass per hectare, right? So you can have a kind of, for a given amount of land devoted to forest, it can be dense, it can be not dense in biomass. And there is, in the paper at least, a weaker sufficient condition for forest biomass that looks very similar to this. So basically, when agricultural technology is sufficiently high forest biomass necessarily declines as productivity continues to improve. Another comment I'll make, which is maybe at this point half-baked, is that this implies interesting comparative statics. So you'll notice that I can express this threshold in closed form, uh, which means you can kind of look at all these objects on the right-hand side of the equation and maybe identify some of them empirically in the pre-industrial data. And that gives you some kind of rich testable implications. So for example, this threshold is increasing in B, it's increasing in C star, it's increasing in F, and it's increasing in A naught. These are all parameters that I introduced earlier. Hopefully I've introduced all of them. There are more to be, but this is just a kind of taste. I think as I go forward, I think this can be used in interesting ways for identification, but in the current version of the paper, I'm not using any of this, just kind of advertising this as an interesting way to derive more empirical tests of the model. Okay. Any questions about this while I'm here?
I'm just wondering the intuition behind this proposition. So when ZA, the productivity of agriculture improves, then the population always increases.
Yeah, so that's right. So I'm kind of focusing on steady states, right? So
Mm,
yeah, you get the population increasing as a
mm,
result. Yeah,
mm.
that's exactly
So
right.
okay, then when population rises, uh,
And that drives
then this
down. So sorry,
proportion, then
that
then this proportion use that the people use more land for agriculture than forestry, right?
so what
But
what what
sorry,
this is saying is that like fundamentally there's an ambiguity there,
mm,
right, in the amount of land that's allocated. So basically, I mean, to try to build a little bit of intuition, yeah, you're exactly right. So we have this improvement in agricultural technology that leads us kind of transitions to another steady state with a higher level of population. The higher population is then going to offset any
mm,
reduction in the price of agricultural goods that you
mm,
would expect associated with an improvement in agricultural technology, right?
mm,
And it totally neutralizes it. That was what we saw previously, right? So ag tech improves, you expect the price to fall, but the population also grows. That increases the
mm,
demand for agricultural output. That offsets the reduction in the price of the agricultural
mm,
good and in fact totally neutralizes it. So then the question is what's going on otherwise? Well, the improvement in agricultural technology increases the return to agricultural land. Um, for the model for the landlord kind of equilibrium condition where we need rents to be equalized, that requires an increase in the return to non-agricultural land, and that's kind of where the interesting stuff is
mm.
going on here. So the question is, how do you get an increase in the return on agricultural land? And basically, what's going on here, right, is that has to come through an increase in or reduction in biomass.
Mm,
That reduction in biomass is going to increase the price of the non-agricultural output, um, not the forest good. I think that was what I've been calling it. And if that price effect is sufficiently large, then you don't need as much of a quantity adjustment, and so you can have this land sparing effect that I described, the kind of
mm.
uh, forest land sparing effect, where improvements in technology actually increase forest land. But if you have a kind of limited price response in the non-agricultural sector, you need a big quantity response, and the consequences that you to kind of get the increase in return on forest land, you need it to be the case that there's actually a reduction in forest
So,
land.
so do you have the utility function of the population or? So I'm just wondering how they divide the expenditure between, agriculture goods and also the other things.
Yeah, it's very simple currently. I'm using a quasi-linear form
Mm,
that's separable in these, and that's
mm,
that's so that's important.
mm.
We go back. I don't want to go too far back. So yeah, it's quasi-linear in CA and CN. The linear part being the non-agricultural consumption good.
Okay. So it's a quasi-linear with CM. Okay.
Yeah,
Uh, yeah, I'm just wondering. So it might be depending on how you think about the period that you are, applying to this model too. But if you go to the old times, I think that the majority of expenditure should be going to food. I
yeah.
mean the agricultural good, and maybe the only small fraction is going to the other things. So maybe it might be good to think about um, you know, you know, I think quasi-linear, specification is a good only when the market that you're focusing on is relatively small to other things, right?
Sure.
Yeah. So, but I think in this case, agriculture agriculture good is so important that it's occupies a huge chunk of the expenditure share. So maybe you might want to think about a bit different kind of expenditure function or.
I totally agree. This
Mm,
was a kind of shortcut to get
mm,
closed form, but solutions. But I agree it's important, and yeah, it makes a difference for sure. It makes a difference for sure.
yeah.
Also the question of separability matters a lot
Mhm.
here. So yeah, I agree. I agree. Okay.
Tristan, can you compute the steady state population level?
Yeah. Yeah, I
I
believe I
think
can.
it would be interesting to see that and how it depends on the environmental parameters, because there would be some interesting testable predictions because we tend to have pretty good data on population. And I think even if you think now, clearly it's beyond the scope of this paper, but if you think in the context of unified growth theory, you have parameters, environmental parameters that might determine a differential timing of the takeoff, and that would be a very interesting thing to add for future work.
Yeah, that makes a lot of sense to me. So I will admit I kind of am aware that unified growth theory exists, but don't know a thing about it. So maybe I'll pick your brain about this. But yeah. Okay. So turning to the empirics, first the first agricultural revolution. So I think, as we all know, right, that the Neolithic Revolution is basically the transition of humankind from hunting gathering to sedentary agriculture. Uh, This, of course, entails a suite of agricultural innovations, and sets off a millennia-long sequence of subsequent innovations. So the disclaimer here is that this is a very zoomed out, high-level analysis that I'm going to be doing, and it's kind of wrapping all of this stuff up into the analysis. I'll if you're unsatisfied with that, I will we'll turn to a specific example after this of a particular innovation. But bear with me for now. So the question here is then, how did the Neolithic Revolution affect local forest cover or regional forest cover? Uh, so a bit on the data. The forest cover data that I'm going to use are forest cover reconstructions for the entire Holocene period. As a plug for this data, it's not my data, but it's super cool. If you're interested in these types of things, I'm happy to talk more about it at the end or whenever. Basically, there's kind of new work coming out from uh, archaeologists, anthropologists, geologists, and the like, uh, who construct harmonized fossil pollen records. That's called the Legacy Pollen 2.0 data set. That's then processed via a model called the reveals model to estimate vegetation cover. So basically, you're going from fossil pollen records that are found in bogs and lakes that can be dated, and using these and using what we know about like dispersion patterns and rates and productivity rates for various taxa um, to construct estimates of forest cover. And in some of these data sets, it's cool. You can actually decompose this into other land use categories. So like agricultural land, grasslands, deciduous, or I think summer green forest cover, evergreen forest cover, so on and so forth. So it's super interesting. There's a lot to be done there. Uh, there are 3,000 roughly sites that are binned into 250-year intervals. So that's the kind of dependent variable. More on that in a second. But for Neolithic timing, I'm using two data sources. The Putterman and Traynor 2006 data, basically based on time when local populations got at least half their calories from domesticated plants and animals, and the Perugian and Fuller 2009 data based on carbon-14 and crop DNA sequencing. So I'm going to use this data to date the Neolithic transition regionally. To motivate the kind of analysis I'm going to do here, I'm plotting two things against the year in BCE. So this is the cumulative for each of these two things, the cumulative post-Neolithic share of forest cover in green, and the share of regions that are in a kind of have transitioned, undergone the Neolithic transition. And the point I want to make with this picture is that there's, as I think everybody here knows, there's a lot of heterogeneity in Neolithic timing. And that's important and allows me to get to identify, in a way I'll describe in a moment, the effect of the Neolithic on forest cover. And you can see that kind of descriptively, there's kind of coincident timing here of these two things, but we'll talk about that more formally. So two problems: there's staggered adoption, and that's a problem if you're thinking about this in the kind of diff and diff type setting. And there's also probably heterogeneous treatment. I'm gonna kind of take the kind of modern approach to this that's from Aaron Dubé and co-authors. This was published this year, in fact. This is kind of a macro micro synthesis methodologically. So they're kind of merging the macro local projections methodology that's been around for a while now with the kind of burgeoning proliferation of diff and diff analyses, and propose this estimator that looks a lot like a local projections method. So I'm basically using as the dependent variable here the growth rate in forest cover at different horizons indexed by H. So I'm going to look at kind of a short horizon, a longer horizon, and even longer horizon, so on and so forth, and predicting this as a function of the kind of Neolithic transition, that's delta NR, time fixed effects. That's necessary because these transitions are happening at different times, and a set of other covariates, which I can talk about more if people are interested. Most importantly, perhaps, is a kind of regional fixed effect that's going to effectively impose that I'm doing these comparisons, which I'll talk about in geographically approximate locations. And then the diff and diff part's coming from this clean controls condition. So I'm not just estimating this equation, but I'm restricting the sample such that each observation needs to satisfy one of two conditions. Either it is a newly treated location, treated meaning undergone the Neolithic transition, or it's a clean control. And by clean control, I mean at horizon H, it has not yet undergone the Neolithic transition. So basically, effectively, what this amounts to is comparing growth in forest cover between regions at different horizons, between regions that have undergone or recently undergone the Neolithic and regions that have not at the kind of relevant horizon of interest. So what's nice about this, just as a plug for this, so this is a relatively simple estimating equation here that solves the many of the problems that have plagued the diff and diff literature historically. And you kind of have, if you're plugged in on this, there's this kind of proliferation of papers that have kind of just tried to solve these issues of staggered adoption, heterogeneous treatment. This approach is dealing with all those things very concisely, which is nice. So what do I get when I do this? I get the picture you're seeing here. So this is plotting years since the Neolithic transition on the horizontal axis. So I'm basically, we know this is staggered. I'm lining up the transition in all these different regions, right? So you can kind of think about it's not calendar time on the horizontal axis. In other words, it's a year since the transition. And on the vertical axis, cumulative change in log percent forest cover. So the measure in the data is the share of region that is covered by forest, and I'm plotting the cumulative change or percent change in that object. I plot years before the transition. Another advantage of this empirical framework is that you can very straightforwardly look at pre-trends to see if there's kind of differential movement between these treated and not yet treated, or the kind of clean control groups prior to the thing we're interested in, the Neolithic. It doesn't look like there's a huge amount, at least systematically, going on here. So that's comforting if we want to interpret this causally. What we then see, right, is over the subsequent 5,000 years after the transition, we see a steady decline in forest cover. It seems relatively unrelenting here, reaching one log point decline 5,000 or 4,000 years out. So see quantitatively large effects on forest cover associated with the Neolithic transition. I'll just say there is like lots of interest among ecologists, ecological historians, and the like in thinking about the relationship between the Neolithic and land use or land cover change. What I kind of like about this, just as a standalone thing, is I kind of applying these modern econometric techniques to try to put a quantitative number on this. Most of the analysis that I've seen, and I have not seen all of it, on this is kind of associational. And I think this at least goes one step further, trying to pin down the relationship between these things. Okay. Any questions about this so far? Okay. So this is the bird's eye view, very, very macro, kind of shamelessly macro level analysis. And what it looks like, just to relate this back to the model, is that there's this kind of, the steady march forward of agricultural productivity seems to have an adverse effect on forest cover, or forest biomass, maybe is the more precise thing to say here. If you're unsatisfied with this, which I think is not wholly unreasonable, I want to complement this with zooming in on a very specific technological innovation. This brings me to a case study of the three-field system. So very different context here, and I'll provide a little bit of background. Around 1000 CE, medieval economies and parts of Europe begin transitioning to a three-field rotation system. I'll refer to this as TFR for the rest of this. What is the three-field system? It basically follows the two-field system, in which you have two fields that are in rotation, rotating between kind of being used for agriculture and being in fallow on alternating schedules. The innovation of the three-field system was, in effect, to, well, move to three fields, but what that means, in effect, is that you have a substantial reduction in time that land is in fallow, not being productive for agriculture. And you can see more on this here. I won't dwell on this, but this is a kind of old depiction of what the three-field system looks like in a time and space grid. lots more to be said about this, but I'll leave it at this for now. Why is this interesting? So we go from basically half of the year land being in fallow to 1/3 of the year, which implies a 33% increase in yields mechanically. That's gigantic historically. The three-field system diversifies weather risk, which is a kind of second order effect on productivity of the system. The introduction of spring legumes is actually good for nitrogen fixing and soil balance. That's another kind of mechanism through which this improves agricultural productivity. Spring oats can be used as horse feed, and horses can be used for agriculture. Spring oats are kind of integral part of the three-field system in most places, and so that's a kind of another effect that this has on agricultural productivity. And so I interpret this as a major shock to agricultural productivity in the medieval era for all of these reasons. So what do we know about the adoption of the three-field rotation system? We know it's geographically circumscribed to some extent. So Mediterranean climates make spring-sown crops difficult. That makes the three-field system difficult. There's also, as I learned this summer, working on this rich historical documentation, most of it kind of narrative, but that's okay, on the implementation of the system. So in England, this is from Gray, 1915. I found this in some library archives, this book, and I realized how much I don't know about the medieval period or agriculture or the combination of these things. So Gray writes, broadly speaking, in the line of the Watling Street form, this is an old Roman thing, forms an approximate boundary between the two large areas characterized respectively by the preponderance of 2 and 3 fields. So I use that in constructing the treated and untreated regions. In France, Marc Bloch has done work on this and describes in detail, some of which I provide here, the regions that adopted the three-field system and the regions that did not. I won't read this, but it's detailed, and there's more detail in both of these cases on what regions adopted. This is not exact, but it's certainly good enough that I can, at least in the case of France, assign kind of a treated or untreated status to departments, and in England to counties. I do that manually based on a reading of these texts, and here's what I get. So blue is a three-field system adopter, and this salmon color is a non-adopter. The dots here correspond to the pollen sites where the forest cover data is coming from. So a few comments on this, right? Spain is effectively a non-adopter here. In France, we see this adoption happening kind of roughly on a latitudinal basis. And in England, we see a bit more complexity. So this is not going to be, so I can kind of get some traction on this that's not explained fully by latitude, which is a good thing. That comes both within England, but also comparing England and France, right? So you see lots of regions in England are non-adopters for geographical reasons that are different from the geographical reasons for why southern France is a non-adopter. So that's helpful. Another nice thing about this is because there's within country variation, I can show you results with country fixed effects, which is aggressive, I think, empirically, but I can do it, and I'll show you those results. Okay, so I'm going to do I don't want to say the exact same thing, but at least methodologically, a very, very similar thing to what I did previously, so I don't have to re-explain much of this. The set of controls that I'm using, yeah, I have them. That condition, they're different. I haven't written it out here. I continue to impose this clean controls condition, so I'm basically getting identification off of a comparison between the evolution of forest cover in the locations that never adopt the system versus the evolution of forest cover in the locations that adopt the system. I'm going to control for a bunch of stuff distance to a Roman road as a proxy for trade exposure. Distance to medieval population center likewise does a similar thing. This is all from the, I think it's the Ancient Worlds Mapping Center data. I'm sure some of you have seen or used this. Also, heavy plow exposure. There's a nice paper in the Journal of Development Economics, I think, that thinks about the effect of heavy plow exposure, which is a innovation that comes about at about the same time as the three-field system. They think about that heavy plow in the context of, I think, economic development, but they propose a way of measuring this regionally. And so I reconstruct their measure and use this as a control to make sure that what I'm showing you in the next slide is not just a heavy plow effect, which just mechanically, I think, is probably more likely to result in reductions in forest cover because, well, heavy plow allows you to till land that you were not able to do previously. So this is a similar picture to the one I showed you before for the three-field analysis. Again, time window. Now I'm actually plotting calendar time, so I'm not getting, there's no differential timing here. Mostly this happens around the year 1000 CE, adoption of the three-field system in the places where it happens. Interestingly, just as a side note here, at least from in England, some of this literature that I was referring to, Gray among others, argue that the three-field system was brought at the time of the Norman conquest in 1066, which is nice because I mean that seems like something we could argue is plausibly exogenous from the point of view of land use. But anyway, so what we see here on the vertical axis is the same thing as before, is the cumulative change in log forest cover. Looking to the left of the transition period, that's the vertical line, we see no evidence whatsoever of pre-trends. But then after the adoption of the system, we see a kind of steady decline in forest cover, reaching, let's say, 0.75 log points if we extrapolate, or if we go out all the way to 1,000 years after the introduction of the system. I'll now show you, just overlay on this some of the robustness checks that I do, which I think are important and interesting. They paint a qualitatively and even quantitatively kind of similar picture. So I add Norway because there's some literature documenting Norway's exposure to the three-field system. I restrict in the blue, I guess, to sites that are near cities to think about sites that are particularly exposed to trade. Why do I do this? Well, to the extent, and I do not think we ought to, but to the extent that we want to think about whether these results would change in the presence of trade, we can look at the blue diamonds for that. I fully exclude sites treated by heavy plow in the green squares. And I think most aggressively, I include country fixed effects. That's the black circles here. So broadly speaking, I think this paints a similar picture. You know, there's kind of marginal significance depending on what specification you like, but this is painting a broadly similar picture to the baseline analysis that I started with that doesn't impose these additional restrictions. So, okay, so that's it. Let me just summarize what we've done to try to leave something in your memory from this. The question I'm after is, did improvements in agricultural technology mitigate or accelerate pre-industrial deforestation? Theoretically, this is ambiguous. But there's this nice cutoff condition such that at high levels of productivity, the ambiguity goes away eventually. Empirically, I tried to show you some analysis that suggests that both at a very high level, from a kind of macro perspective, agricultural technology tends to lead to deforestation, and then zooming in on the three-field system, which might be more germane to my model, my model's concept of agricultural technology, we see a similar thing qualitatively. So that's it. Thank you so much. And as I said, this is very preliminary stuff. So I would love any feedback. And thanks again for inviting me. I, yeah, value your all's feedback on this tremendously. So thank you. Happy to take questions if people have them.
Yeah, can you just give me some more intuition on the various forces? Intuition now, not. Uh, Suppose we double agricultural productivity, uh, so the existing land can sustain twice as many people. Why does that necessarily? Why does that ultimately, that kind of thing, ultimately imply deforestation? Is it population is growing and needs the land in your model? Or is it that energy requirements require cutting down more trees? That it's forcing it. Ultimately, you're saying it forces this. I don't see why that's true. Just
Yeah, so
intuitively. Why can't everybody just move to cities and then, all the extra people and not take up any more land? Um, that's sort of what I'm wondering about. You've got an ultimate, you've got an ultimately it's going to lead to deforestation, and I just don't quite have that.
yeah, so basically, okay, so a few things. The population thing is important, right? In the absence of Malthusian population growth, right, the improvement in agricultural technology, we expect to reduce the price of agricultural output, which can certainly have the effect of disincentivizing, and this is kind of the kind of stylized graph I showed you before, disincentivizing expansion into forest land, because if the price falls sufficiently, uh, with the Malthusian population dynamics, that goes away entirely. They fully offset, the growth in population fully offsets the the fall in price of the agricultural good that we would otherwise expect.
But
Uh,
yeah, but wait, it sounds to me though, like you have an implicit assumption that um, there's a certain amount of land required per person, and I'm suggesting maybe that's not true. That if all the extra people move to a city, they don't take up any more land, basically. It's a negligible amount of land.
yeah,
Is that true? Have I got it right, or am I missing something?
I'm trying to think about the question of whether there's an implicit assumption about land requirements. My inclination is to say there's not an implicit assumption, but I wouldn't swear by this. There is not there is not an explicit. Yeah, I don't know. I don't know
Yeah,
if that's kind of showing up in here somewhere. But I think that's the key thing. Like, you would get potentially a much larger region of ambiguity in the absence of these Malthusian population dynamics. And there's other stuff going on the non-agricultural side. Um, so, you think about, yeah, there's a few forces going on there, but I think the main thing that like makes this germane to the pre-industrial setting is the population dynamics, which mechanically drive up the price, offsetting the reduction in price we'd otherwise expect.
I thought
yeah,
that the answer to John's question is that you need a subsistence consumption of agricultural product. Isn't that it?
yeah. But if I increase the productivity, I get that. I get that increase in agricultural product. What I don't
Yeah.
see is why we ultimately have to have deforestation. That's what I don't see. It seems to me that that I'm making a distinction between the number of people and where those people live. A simple model just says there's more people, so they cover more space, and I'm saying, well, maybe that's not true. Maybe more people don't cover more space. In
Yeah,
fact,
it,
that
but
see
John,
that. Yeah, go ahead.
but yeah, more people means more consumption of stuff. So even if they're all in cities, right? Like unless you have, unless you, yeah, more consumption of stuff, of food in particular,
Sure, sure.
right?
But
But
that's
is
why
but
the productivity provides that. That's why I don't see the ultimate. You've
but
got you've got this thing that there's some force that you're saying ultimately leads to deforestation, and I don't see why that's true.
but I think this then gets back to the basic ambiguity. I mean, you know, if okay, so everyone's in
Yeah,
a
yeah.
city and we agree that, you know, we agree that this frees up land, but then you need more food. That in order to produce that, it's not clear in the presence of, so it's not clear in a more general model than this one, I think, if
Well, your model delivers the results, and I'm not arguing that there's anything wrong with that.
yeah.
What I'd like to see is a little more discussion of the intuition that addresses the question I just raised.
So let me try one more time. Like so you're kind of thinking, okay, we have this improvement in
Yeah, suppose the world consists of the island of England,
yeah,
or Britain.
yeah.
Okay, so there's no more land. It's all being used, but we double productivity. Okay, and so half of England is forested, but we double productivity. Why do I have to cut down any more trees? If everybody moves to a city, all the new people move to a city. So they all move to London. That's sort of a real quick intuition of what I'm thinking about.
But you don't have to. It's that it's kind of the profit motive of the person who's in charge of the land, right? Or who's making the decision about land allocation. That's kind of at the core, I think, of this. It's should we, you
Oh,
know,
hmm.
right? So
Well,
like,
perhaps. I guess what I recommend is that you develop that. So
yeah.
you have a sort of a verbal intuition as to what's going on that addresses the question that I'm asking.
So if I can jump in,
Yeah,
I
please.
I think one way to help answer John's question, and I'm going to give you the same suggestion I gave you in the brown bag a few weeks ago. Do an analysis where there's this opening to trade in historical times. Um, because then your model has very different implications because now the price doesn't respond in quite the same way. Price elasticity is different. And I think the historical case that I had in mind was the opening or the development of the Grand Canal in China, which suddenly opened trade between the North and the South and had a very, massive impact on our economy. Yet, and I think John may be right here, it's not clear to me what happened to deforestation in that case, because that was also associated with the rapid rise of cities.
Yeah.
So I think something like that might help build the intuition further and address sort of John's ultimate concern here.
Yeah, I think these are good comments, and yeah, I agree. Like, I don't think I have. So I think I understand the intuition for the agricultural side quite well. There's stuff going on the non-agricultural side which is more complex, which I'm kind of still wrapping my head around. But on the agricultural side, it's this basic thing where I am a landowner. I have some amount of land. I can decide whether to convert it to farmland or keep it as forest. Like it is not obvious what I should do when productivity increases. On the one hand, I can, with the same amount of land under tillage, produce more stuff. And therefore, I don't need to go into the forest land. And I might even be able to reduce the amount of, and I think, John, this is your intuition, might be able to reduce the amount of farmland that I'm using and kind of let some of it regrow and still produce the same amount of food. But the question is that the best, the most worthwhile use of the land? And that question depends on the price elasticity of demand, whether I will optimally choose to allocate my land to forest or agriculture, following an increase in agricultural productivity.
Okay.
Tristan, could you go back to the slide that shows the model?
Yep. Sorry, this will take a while.
It's okay, yeah. Yes.
Do you want this?
Yes, this one, yes. So I was also thinking about the same question as John. So suppose that productivity doubles, and then as you said, ultimately the population doubles, say, then what happened is that there should be larger demand for non-agricultural sector. So do you think that output of the non-agricultural sector also doubles or less than doubles?
That's a good question.
Yeah. So that's in the end there's a shrinkage of forestry, which means that give Uh, I think that demand for non-agricultural sector would rise if other things are being equal, but that will require more forest for feed the energy, right? But
Yeah.
somehow this is mitigated by some force. Maybe HA and HN. What are these?
So those are late. That's labor, and I should have said here
Labor.
what I'm
Okay,
doing.
okay. Maybe the labor with is might be moving more to no agriculture sector. That might be related to what John said. So the people are moving to cities, doing other things than agriculture, and which could increase the
Yeah.
productivity of
So
cities. Yeah.
Oh,
yeah.
well, I
So
definitely had without it saying so, I hadn't even thought of it that way, but I was definitely
Mm.
assuming that you could move people from one sector to another,
Mm.
by saying that they move to cities where they're not in agriculture anymore.
Yeah.
That's definitely what I was thinking about. So
Right.
so
I
John,
hadn't thought of that. So you have HA and HN are fixed.
yeah, that's right.
Uh,
They're a share of
that changes.
population.
Oh, yeah. That's probably intuitively the answer to my question.
And
Mm.
L increases because the
Yeah.
population
Yes.
increases
Yes.
L. So that you have one factor that remains constant, but
Yeah.
the other one that changes with the increase in productivities. And so naturally, you would be led to chop down
Hmm.
more trees.
Mm.
Yeah. Okay.
So in a sense, I think this, it will be, beneficial to show that how these all variable changes when the GA increases.
Totally agree with
You
that.
are
Yeah.
only focusing on the forestry, but all things are moving in this model. So if you show that in the figure, that should be very, I think beneficial for the readers.
So I agree. I want to point out one other thing just to emphasize this, and this is all really helpful for me, just as an aside. Um, the it is not, I think I phrased it this way. Maybe this is misleading, and I'm kind of getting, maybe incorrectly, that people are taking it this way. I say deforestation is inevitable here. John, I think, was focusing on this. What I mean by that is that, right, as ZA gets large, the effect of additional ZA will
Mm.
be negative on forest cover. That's different from saying that
Mm.
the model kind of trivially implies that
Oh, okay.
improvements in ZA reduce forest cover, because that is certainly not the case. What the proposition
Mm.
here says, right, is that indeed at low levels of ZA, the exact opposite happens,
Okay. Yeah, yeah.
right? You get increase in forest cover as
Mm.
agricultural productivity increases. My point was
Mm.
basically delineating low ZA from high
Yeah.
ZA. Yeah.
So I think it is numerically easy to show that the response of all the variable against GA. So
Yeah, it's very easy to do. I agree, and I should have done this, and I think it would be
mm,
helpful for. I mean, I'm like I said, I'm kind of still. I have some intuition for parts of this, but not. I'm not fully there yet,
mm,
and I think that's a good way to get
mm.
there. So yeah, that's helpful.
It might make sense and might be helpful to talk explicitly about the marginal product of land in agriculture, and the marginal product of H. I don't know if land is the right term, but marginal product of HA, marginal product of HN, and how does that depend on the exogenous component Z and on the endogenous ones that change in response to the changes in Z.
Yeah.
So that would allow you to track the dynamics and understand the causality of all these things better, I think.
Yeah. Yeah, I agree with that. Yeah.
Okay,
Any other
so
questions?
I think there are no other questions. No. So thanks a lot, Tristan, for this very nice presentation. And
Thank you so much for inviting me. This is a real pleasure. Yeah.
also, we are happy if you join our group because
I'm happy to join it too. Yeah.
we try to organize seminars twice a month,
Okay.
average. So if you have time, we are very happy to have you in our group. So thank you once again, Tristan. And yes, we have no planned seminars this month, but we will have something in January.
Okay.
I will send email very soon.
Great. I'll plan to be there. I was hoping to make it last week, or 2 weeks ago, but I wasn't able to. But you can expect to see me in these. This is fun.
Thanks.
Thank you all.
Thank you very much.
Thank you. Ciao.
Thank you very much. Bye.
Bye.
Thank you. Bye.